Hello everyone, in this video we are going to be taking a look at the complex function of z defined as a² minus z² to the power of a half, where a is a positive real constant. Now because this function f has a power of a half in it, that immediately suggests that we're going to have some issues with multi-valuedness, and so what we're going to do in this video is firstly identify the branch points of the function, explain why they're branch points, and then talk about some possible ways to introduce branch cuts to turn this multi-valued function into a single valued function. Now I'm choosing to focus on this particular function of z basically because there's a specific contour integral that I would like to cover in my next video, and this is sort of prerequisite knowledge for that. However, this video should still be useful more generally if you want to improve your sort of intuition and understanding about branch points and branch cuts. So the first thing I want to do with this function is split it up into two factors using difference of two squares, right? So it's a² minus z² to the half. We can write it as a plus z to the half, and then a minus z to the half. Now if we show the real numbers a and minus a on an Argand diagram, as I've just done here, we can come up with a nice interpretation of each of these factors, a plus z and a minus z. So basically, if we take some arbitrary complex number z, let's just put it over here, it could be anywhere in the complex plane, then consider the sort of vector that takes you from the real number minus a to this arbitrary complex number z, and that vector would be z minus minus a, which is z plus a or a plus z, and therefore the first factor in our f of z, a plus z, is the complex number slash vector that takes you from minus a to z. What about the complex number slash vector that takes you from a to z? Well, that would be this one here. That would be z minus a, which is almost the same as the second factor in f of z, except the a and the z are switched around. So just so that we can have a nice consistent interpretation of these two factors, what I'm going to do is keep the first factor the same but flip the terms around, which is not really doing anything. But for the second factor, I'm going to take out a minus sign, write it as minus z minus a, all to the power of a half, so that then this z minus a is the complex number that takes you from a to z. So what's actually the point of doing that? Well, the point is that we can switch to a polar representation for each of those complex numbers that describes where z is relative to minus a and relative to a. So to switch to polar representations, we need to introduce some angles and lengths on our diagram. So I'm going to define this angle here as theta minus, and this length here is r minus, and predictably that angle there is going to be theta plus, and this distance there is going to be r plus. So then z plus a can just be written as r minus e to the I theta minus, and that's all to the power of a half. And then we've got minus r plus e to the I theta plus, all to the power of a half. So then we want to put this entire expression into modulus argument form by collecting the prefactors at the beginning and then just having some complex exponential. So note that r minus and r plus are both positive real numbers by definition because they are just distances, right? They're just lengths in the complex plane. So what you can do is take your r minus to the half and r plus to the half and just stick them at the beginning and put them under a square root. So you've got the square root of r plus r minus at the beginning. Then you've got e to the power of some stuff, and you're going to have a half I in common. You are going to have theta plus theta minus. But the one thing I haven't taken account of here is that minus sign. So I'm just going to stick that at the end for now and do minus 1 to the power of a half. We can make this look a bit better by writing the minus 1 in modulus argument form and then combining it with the complex exponential bit. So note that minus 1 is e to the I pi, but it's also e to the I times 3 pi or e to the I times 5 pi, or indeed e to the minus I pi, e to the minus 3i pi, and so on. So in general, minus 1 can be written as e to the I times some odd number, which we can write as 2n plus 1 times pi, where n is just any integer. So then remembering that that's all to the power of a half, you combine everything together to get the following expression: square root of r plus r minus, and then e to the half I. You've still got your theta plus theta minus, but now you additionally have this plus 2n plus 1 pi. So just to summarize, all we've really done so far is rewritten f of z in a different representation. We've written it in polar form in terms of the moduli and arguments of z relative to the points a and minus a. So what's the point of doing that? Well, the point is that it allows you to show that a and minus a are branch points of the function f of z. So the way this works is you imagine moving around a path in the complex plane that encircles, first of all, let's say the point A. So it could be a path that looks something like that. Doesn't have to be a perfect circle, it just has to start somewhere in the complex plane, go all the way around A and come back to where it started. Whereas a path like this, for example, would not be what we're talking about because it doesn't go all the way around A. So let's say you start here and you go all the way around. You can see that, well, r plus may or may not be changing depending on whether we're moving in a perfect circle centered on A or not, but definitely theta plus is going to be changing. Originally there's some angle there, and theta plus is going to keep increasing. By the time you get back to the starting point, it looks like it's the same value, but it's really 2 pi bigger than it was at the beginning because you've gone around a full circle. So let's write that down. If you circle around A, what happens is theta plus becomes theta plus plus 2 pi. Notice that if you're only circling around A and not minus A, the same cannot be said for theta minus, right? Theta minus just comes back to its starting point because you haven't gone all the way around the point at minus A. The significance of that becomes clear when you substitute theta plus plus 2 pi in place of theta plus in our polar representation of f of z. Essentially what we're doing is adding an extra 2 pi to the phase term in the complex exponential. So if you add an extra 2 pi into this bit here, it's mostly going to be the same as what it was before, but you've got an extra factor of e to the half I times 2 pi. So what is going to happen is that what was originally f of z is now going to turn into e to the half I times 2 pi multiplied by f of z. E to the half I times 2 pi is e to the I pi, which is just minus 1, and therefore f of z turns into minus f of z when you move in a complete loop around point A. So we've therefore shown that A is a branch point of the function f of z. A branch point is basically exactly what we've just discussed. It's a point such that when you circle around it in the complex plane, the function doesn't return to its original value. You can see pretty easily that the same arguments would apply to the point minus A as well. If you circled around the point minus A, then theta minus would acquire an extra phase of 2 pi by exactly the same logic, and f of z would turn into minus f of z as well. So we could stick a plus or minus here, turn all these pluses into plus or minus, and then from here on it's the same because you're just adding an extra 2 pi into the phase factor in your complex exponential. The next thing that's interesting to consider is what happens if you circle around both points in one big loop. So for example, maybe you start up here and you go all the way around A and minus A like that and come back to where you started. So in this case, you're basically adding 2 pi to both theta plus and theta minus. So overall, you've added 4 pi to that complex exponential bit. So what's going to happen is f of z is going to turn into, or it's going to acquire an extra factor of e to the half I times 2 pi plus another 2 pi, like that. And then this is e to the half I times 4 pi, which is e to the 2 pi I, which is just 1. And so f of z doesn't change. It stays as f of z if you circle around both points in the same loop. So the conclusion is that we don't want to circle around a or minus a individually if we want f of z to be single valued. However, it's fine to circle around them both at the same time. So that leads us to the concept of branch cuts, and a branch cut is basically just a line that you introduce into the complex plane that you agree that you're not going to cross, right? If you imagine the complex plane as like a big sheet of paper, then a branch cut is basically where you take a pair of scissors and just cut out a line so that you can no longer move from one side of the gap that you've created to the other side. There are various possible branch cuts that we can introduce for this function to prevent this issue of multivaluedness. Remember that the main issue is that we want to stop ourselves from circling around either of the branch points individually, but we can circle around both of them at the same time. So one option would be to make a cut there and a cut there, where each of the two bits of that branch cut goes off to infinity, because then however hard you try, you can't make a full circle around minus a or a, because you're always going to run into one of those branch cuts. You could, instead of doing them horizontally, you could do them at any angle you wanted, like that, or like that, or whatever. But it's usually easiest just to put them along the real axis. However, it's equally okay to just put a finite cut between minus a and a like that, because then you can't circle around minus a, you can't circle around a, but you can circle around both of them at the same time. We showed earlier that that's okay to do. So that would also be a valid choice of branch cut. So we've sort of resolved this multi-valuedness by introducing one of these potential choices of branch cuts, but this is not quite the full story, because we still have the issue of, well, how do we know in each particular bit of the complex plane, how do we know whether f of z should be positive versus negative, for example? So I want to spend the remainder of this video discussing branch points from a slightly different perspective, give you a more full understanding of what a branch cut really is, and resolve this issue of how to actually calculate unambiguously the value of f at any point. Right, so the first step in this analysis is to split up the complex plane into 6 regions, as I've shown in this diagram here. We've basically drawn the 4 quadrants relative to the 2 branch points, a and minus a, and thereby created 6 regions in total, which I've labeled A to F. So we're going to try and actually calculate the value of f of z in each of these regions, not at an arbitrary point in each of the regions, but just next to the real axis in each of these regions. So for example, we might choose a point here in region A, a point here in B, here in C, and then here in D, here in E, and here in F. So we're just focusing on z being a complex number that has an infinitesimally small imaginary part. This might seem like a bit of a random thing to do, but it is going to make sense if you stick with it until the conclusion. In order to actually specify the value of f of z, we need to decide or agree on a range of values for both theta plus and theta minus. So we're going to just decide for the time being that theta plus and theta minus are both going to be restricted to the range 0 to 2 pi. So let's say now we restrict theta plus or minus such that 0 is less than or equal to theta plus, and indeed theta minus, which is less than or equal to 2 pi. Note that 0 and 2 pi are not equivalent here because of this multi-valuedness issue. So if we're interested in f of z in each of the 6 regions, we need to go around and think about the value of theta plus and theta minus in each of the 6 regions. So I've just put some gaps into my diagram that we're going to fill in for the values of those angles. So let's start with region A, theta plus. Remember, we're only focusing on a point which is basically on the real axis, just a tiny bit above the real axis. You can see from the diagram that if we're on the real axis and in region A, then theta plus is going to be 0. By the time we've moved into region B, we've sort of done this, right? We've moved on to the other side of point A, and therefore theta plus is now pi. In region C, it's the same story, it's still pi, and it is still pi in region D. And indeed in region E, things only change when you come back from E to F. You've gone all the way around now, and theta plus is basically 2 pi. How about theta minus? Well, theta minus also starts at 0 in region A because you're over on the right hand side relative to the point at minus a. You're still on the right of minus a in region B, however, so theta minus is 0 here. Then you've gone over to the other side of minus a by the time you've got to region C, so theta minus becomes pi. Then it's still pi in region D. Then you move back over to the other side of minus a when you go from D to E, but you've now gone all the way around, right? So theta minus is 2 pi there, and it is still 2 pi in region F. So let's do some substitution and actually come up with simplified versions of f of z in each of those different regions. Remember that because we are focusing on values of z that have infinitesimally small imaginary parts, we can basically say that z is just some real number x, right? So in region A, what is f equal to? Well, we start off with our square root of r plus r minus. R plus and r minus, remember, are the distances, the positive distances, right, from your point z, which is on the real axis, to each of the points a and minus a. So if we are over here in region A, then the distance to the point at a, right, is just x minus a, whereas the distance from our point z equals x to the other branch point minus a is going to be x plus a, right? So our root r plus r minus can be written as root of x plus a times x minus a. Then we have got our phase factor. It's e to the power of, now in region A we agreed that theta plus and theta minus were both 0. So these things both become 0, and then you've got half I times 2n plus 1 pi, which is the same as just n plus a half times pi times I. So let's do e to the n plus a half pi I. Then you can expand the brackets and note that e to the half pi I, so e to the half pi I, just that bit there, is the same as just I itself. And so you can write that as e to the n pi I times I times the square root of x squared minus a squared. So I've just gone through the whole procedure doing the same thing for regions B to F as well. It would have been pretty boring for you to watch me write all of that stuff out because it's basically doing almost the same thing again and again. So you've got all of the details written out for regions A, B, C. I have skipped some of the working for D to F because it's largely the same as A to C, and the distance factors are the same. It's just that the phase factor is changing a little bit each time. So as a result of going through all of that, we've now almost unambiguously specified the value of f of z in each of those regions just above / below the real axis. There's still an ambiguity because there is this value of n that appears. All of the results have this e to the n pi I factor in them. Remember that n is just any integer, but there are only really two different values that e to the n pi I can have, right? If n is even, then it's 1. If n is odd, then it's -1. So e to the n pi I is either +1 or -1, depending on which of the infinitely many values of n that you choose. Now that ambiguity can't really be resolved. That's just something for us to decide, right, which value of n we want to take. What matters really is the relative sign of these various different expressions compared with each other. So what I mean by that, for example, is let's say that we just decide that in region B, we want the value of f of z to be positive. So if we decide that we want it to be positive in that region, that means e to the n pi I has to be -1 to cancel out this minus sign in the beginning there. And therefore, you would have to have a -1 up there in your expression for f of z in A. And therefore, if f of z is real and positive in region B, then f of z has to be negative and imaginary in region A. I'll just mention now that that relationship between the results for regions A and B is going to be particularly important for my next video. But the key point to take away about these e to the n pi I factors is that basically all of the results for f of z have this plus or minus ambiguity, but you just have to choose your pluses and minuses in a consistent way. So the other thing you're probably wondering is, what does this have to do with branch cuts? Well, examine the values of f of z. First of all, in regions A and F. So you're comparing that with that. If you look at those, you will see that they are exactly the same, right? So if you go from region A to region F, in other words, you go from just above the real axis here to just below the real axis, nothing interesting happens. The function is continuous in that region, and that's all fine. What if we were to do the same thing in regions C and D? So you compare this and this. Again, you notice that they are exactly the same. So go through the same explanation, going from here to here, there is no discontinuity in the value of f. If, however, you compare the values of f in region B and region E, which is basically going from here to here, you'll notice that you've got a minus sign at the beginning in the expression for B, but you don't have that minus sign in region E. The expressions are otherwise identical, but they just differ by a minus sign. So if you go sort of across the real axis going from B to E, the function suddenly changes from being positive to negative or negative to positive. So the fact that you have a jump in the value of f of z when you cross that line, which is the boundary between B and E, but you don't have a jump in the value of f and z going from A to F or C to D, implies that restricting the values of theta plus and theta minus from 0 to 2 pi is equivalent to putting a branch cut in this finite region between minus a and a. So this is what I meant when I said earlier that I was going to give you a different perspective on branch cuts. You can think of a branch cut as being equivalent to restricting the argument of z relative to the branch points to a certain agreed range. And once you've agreed on that range, you are then restricted to make sure you choose consistent signs for f of z in the various different regions of the plane. Now, an interesting exercise would be to prove what I've just written down here, which is that if you choose a different restriction for the two angles, in particular, if you require theta plus to be between 0 and 2 pi, but theta minus to be between minus pi and pi rather than 0 and 2 pi, you find that there's a discontinuity in f going from region A to F and region C to D, but not B to E, and therefore restricting the angles in that way is equivalent to making the other type of branch cut that we discussed earlier, where you have sort of a half line extending off to infinity on the positive and negative real axes. I won't prove that here because it's going to take quite a lot of time. However, you can do it using exactly the same method that we went through for the finite branch cut. So anyway, I hope you now feel that you have a slightly more in-depth understanding of branch cuts and you are ready to use these results to do some contour integration. So I'll see you soon.